Hello physics students, it's Mr. Kennedy here. Hope everybody's doing great. I'm going to take you through something called series circuits today. We looked at a little bit about circuits the other day with Ohm's law and the power equations and all of those things. Now it's time to take a look at what happens when we start to put elements together. And a series circuit is a circuit named series because the elements come one right after the other. So if I were to draw this, let's say I have a battery right here. That's our battery. And then here's an element. These are resistors. And then it comes back. So when something's in series, what that means is that you go from one to the next to the next. You have to go through this resistor to go through this resistor to go through this resistor in terms of current. The current leaves the battery, it has to go through this resistor, then this resistor, then this resistor to come back to where we started. So these elements are one right after the next. The current has to pass through each one before it gets to the next one. That's why we say they're in series. Series meaning one right after the next. Now, let's actually give these some titles here. Let's call this VT. That's the total voltage of the battery. So that's the energy that the battery is going to give to the circuit. Technically energy per charge, but you can just think of it as energy right now. We'll call this resistor 1, call this resistor 2, and call this resistor 3. Now, when we do this, we're going to get a couple properties out of here right away. But I want to emphasize that we're going to need some of the things we did before. And you might remember I talked about that coin that my father used to have. So let's actually make that little coin up here. Voltage is current times resistance. V equals IR. So having that in our back pocket is going to be really useful. And later on we'll pull out the one for power as well. So when we look at this, because if we think of it as water flowing, if current's going to leave the battery, pass through this resistor, and then this resistor, one of the things about this that's kind of annoying with series circuits is if one of these were to fail, or if this wire were to fail, let's say that there was a break in the wire right here, now there's no longer a circuit. Maybe these were 3 light bulbs, one light bulb, the next, and the next. If one of the light bulbs burns out, then the whole circuit goes out. So you don't see your home, for instance, hooked up in series because you don't want to have everything running at the same time. There are elements that might be hooked up in series, but generally a good example for this is the old Christmas lights, where if one of them burn out, the whole strand burns out. That was kind of annoying. In fact, I spent a lot of time when I was a young kid checking light bulbs to make sure with a conductivity meter that they were actually operational. So not exactly a Merry Christmas, but anyway. But one of the properties of that, because there's only one place for current to go, it can only go through this wire, through this, and then this, that the current in this must be the same. So the current total, the current that comes out of the battery, must be the same as the current through resistor 1, must be the same as the current through resistor 2, must be the same as the current through resistor 3. All 3 of these must have the same current going through them. There's no difference. There's only one current that goes through there. But what happens is some of the energy from the battery, so the charges leave and they've got a certain amount of energy, you'll lose some of that energy through the first resistor, you'll lose a little bit more through the next resistor, and a little bit more through the last resistor, which means that if I add up all the energy lost here through these things, technically given away as heat, this should be the same. In other words, the total voltage of the battery must be the same as the sum of the 3 voltages lost through the resistor. So we start here with a certain amount of energy, lose a little bit here, lose a little bit here, lose the rest here, and then you return back to the battery with nothing. You can't come back to the battery with extra energy. You can't make it all the way around if you don't have enough energy, so you have to end up with nothing. But these 2 equations are important because they're going to help us solve problems with these circuits. And if we go up to our little circle here, because V is equal to I times R, I'm going to make a little replacement. In terms of V total, it's I total times R total. V1 is I1 times R1. V2 is I2 times R2, and V3 is I3 times R3. That's a 3. Now, because of this, because we know that all the currents are the same, the currents just drop out. And what you find is one of the most simple rules for resistors, that if you have them in series, the total resistance, you just literally add up the resistors. You add up the resistors, and that's it. That's the resistance you have. So let's take an actual example. I'll make this a really simple example, but it works for anything. And we'll see what happens here when we actually try it. Now when we do this, I'm going to do this work right on the diagram, or quite a bit of it on the diagram. And I think it's a little bit easier that way to keep track of what's going on. So let's take a look at another circuit. Again, the numbers I'm going to use are really, really easy here. So here is resistor, 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 and then I'm going to have my battery right here. And like I said, I'm going to make these numbers really nice. I'm going to say this is a 6-volt battery. This is a 1 ohm resistor. This is a 2 ohm resistor. And this is a 3 ohm resistor. And the questions I'd like to have for this circuit: what's the total resistance? What is the total current? What's the voltage, current, and power through each resistor as well? So again, I want to know what is the total resistance, what is the total current that leaves the battery, and then what's the voltage, current, and power in each resistor. Now remember that it is really useful for us to have those little circles here, little coins that I call them. V equals IR, that's going to help. And then the next one, P equals VI. And we're going to see what we can get from this. And again, I made the numbers nice. You won't always have nice numbers, but this is going to help us at least get the feel for it at the beginning. So first off, what's the total resistance? Well, the total resistance is just going to be us adding these together. I've got 1 ohm, 2 ohm, and 3 ohms. So that means the total resistance here is going to be 6 ohms. That's where you should start. Start it with what is your total resistance. Now, let's find the total current. That's kind of our second big step. If we look, current is voltage divided by resistance. So the total current is going to be 6 volts divided by 6 ohms. That's 1 amp. Once we know this, the rest of this problem is actually really easy because we know a bunch of things about this. So we know that we're going to have current leave the battery, 1 amp of current. As it leaves the battery, when I want to find the current through each one, I know that the current's the same in every single one because there's only one place for it to go. It has to go through this resistor, then it has to go through this resistor, and then through this resistor. So this must have 1 amp of current, this must have 1 amp of current, and this must have 1 amp of current. Notice I did the work right on the diagram. I think it's easier that way. Now let's find the voltage in each particular resistor. I'll use a little bit of a different color here, but I know that voltage is current times resistance, I times R. Well, I know that this is the current, that's the resistance, so I know that I times R, this will have 1 volt that I have to pass through. It takes 1 volt of really the energy to pass through there. In this one, 1 times 2, that's 2 volts that it has to pass through. And then 1 times 3, that's 3 volts that it takes to pass through. So in this particular situation, the hardest resistor to get through is the one with the biggest resistance, which makes the most sense because it takes 3 volts to get through there, takes the most energy to get through there because this is providing the most resistance to that current. This one's the easiest one to get through. 1 volt means it's easier to get through. And here's how you know you've done things correctly. The voltages should add. So the currents are all the same, but 1 volt plus 2 volt plus 3 volts adds to 6 volts. I know that I did that correctly then. Now let's look at the power output. In the power output, we can figure out what's going on with that too. I'll use that a different color as well. Power is voltage times current. So voltage times current, 1 times 1, that gets me 1 watt. 2 times 1 gets me 2 watts. 3 times 1 gets me 3 watts. So when I look at this, I can just, again, use those basic rules and those basic coins that I had to find out most of these things. But we can start with the total resistance. 1 plus 2 plus 3, that gets us 6. 6 volts divided by 6 ohms, that gets us total current. Current is the same in every circuit, so they all get 1 amp. 1 times 1 gets me 1 volt. 1 times 2 gets me 2 volts. 1 times 3 gets me 3 volts. But then I can use P equals VI. 1 times 1, it gets me 1 watt. 1 times 2 gets me 2 watts. 1 times 3 gets me 3 watts. Now, a question that comes up somewhat regularly is, what if these were light bulbs? If these were light bulbs, which one would burn the brightest? Well, when you're looking at which one burns the brightest or gives off the most energy, it's always the one with the most power. So notice this would be the one that gives off the most energy. If it were a light bulb, it would give off the most power and therefore it would burn the brightest. So you can see that series circuits are actually pretty simple. Keeping your basic rules that the current is the same in the series circuit and that the voltages add will give you pretty much everything you need. Now the numbers, again, you may see in some of the worksheets and everything may be a little bit more involved, but the pattern is still the same. So give a few of those a try and let me know if you get stuck in anything, and feel free to email me with any questions you have. All right, everybody, hope you have a great day.